Welcome, everyone, and thank you for joining us today. My name is Kara, and I'm with the Ohio LTAP Center here at ODOT, and I'll be your host for this webinar. Today's webinar is titled Investigation of Innovations in Mounted Attenuators for Safety in Work Zones, and we're excited to have Mohit and Rex as our presenters. Before we begin, I'd like to cover a few housekeeping items to ensure a smooth webinar experience for everyone. If you have any questions during the presentation, please use the questions panel on your screen. You can type your questions there, and we will address them during the dedicated Q&A session at the end. If you're experiencing any technical difficulties or have any other issues, feel free to use the question panel to communicate with our team, and we'll do our best to assist you. Please be aware that this webinar is being recorded. The recording, along with a PDF of the presentation, will be emailed to all registered attendees after the session. If you are logged in and present for the full duration of the webinar, you will receive a certificate of attendance within 5 business days. All right, with that out of the way, let's get started. It's my pleasure to hand it over to Mohit. Mohit, the virtual floor is yours.
Thank you, Kara. Good afternoon, everybody. I'm Mohit Mandakot. I'm the engineering manager here at the Transportation Research Center. I had the privilege of being the PI on this research program titled Investigation of Innovations in Mounted Attenuators for Safety in Work Zones. Rex, our next slide. I want to take a minute actually to stop and introduce Rex Nagel. Rex, hop on in and introduce yourself as we go through these slides.
Hello, everybody. My name is Rex Nagel. I am a project manager out here at TRC in the Advanced Mobility Division. So I have the privilege of working with Mohit and several others on our team. So looking forward to presenting a little bit more on this ATMA system today for you guys.
Perfect. Let's dive into the project. A little background on the project. The idea of the program was to uh, evaluate broadly innovations that will support safety for the operators who are out in work zones. Now, um, the biggest component of working out in the open with traffic flowing at you is that we're putting our work crew at high risk due to errant traffic behavior, and it is that particular uh, problem that we try to figure out and solve with our research. Are there innovations out there that will help reduce the risk to our work crew as they expose themselves and work at these work zones? The research team here was strategically formed of tier C personnel, a couple of our partners to help solve that problem from a wide variety of perspectives. Before we dive further into the project, I want to take a minute and introduce TRC Ohio to folks who may have not heard about us. TRC Ohio, we are the nation's largest independent proving ground. We are in East Liberty, Ohio, about 45 minutes northwest of Columbus, and we operate this large research and test center that focuses with its primary mission being on safety. We here at TRC test and research technologies before in our controlled environment before they ever go out on public roads with the desire to focus on whether these technologies can provide the right safety benefits when they are finally deployed on public roads. We do that with our 3 E's. I like to call them 3 E's. It's the earth, the 4,500 proving ground that you see in front of you, 20 odd buildings, 4 labs, hundreds of individual test features to help evaluate vehicle safety as well as roadway safety technologies. Our expertise, our people, are the second E. Hundreds of research scientists work at Transportation Research Center, supported by engineers, program managers, technicians, and all of those people work in unison to help solve the problem of safety. And then the last piece, and not unknown, is the equipment, the third E. As you will start to see this project get displayed in front of you, you'll start to see how all of those three E's came together to help evaluate if there are technologies out there that can help keep workers safe when they operate in work zones. Next slide. A big part of the program was to leverage the Smart Center to test and evaluate candidate technologies that may have the potential for safety. Uh, the Smart Center, which was opened in 2019, is a dedicated, one of its kind, connected and automated vehicle testing facility here in Ohio. It's got 540 acres of dedicated highway as well as urban network sections that help you test scenarios that these technologies may see out on public roads without having the exposure, the risk of deploying these technologies out on public roads. So, this is a dedicated proving ground area that has a 6-lane high-speed intersection, configurable traffic signals to help figure out various scenarios. It's got a fiber network and V2X communications that allow for testing of connected and automated vehicles on our facility. Next slide. Now we used all of these resources, facility, and technologies to help figure out what's happening in the work zones. As these particular charts tell a story, over the last decade or so, the work zone fatalities are trending in the wrong direction. You can start to see a slow and gradual increase in both fatalities that you see out in work zones as well as serious injuries. And as you dive into this further, a large proportion of these fatalities are the rear end collisions that occur in work zones. So our first target was to figure out uh, how can technology help reduce the severity of these impacts. And so we narrowly focused on the truck mounted attenuators that stay within the work zones and provide a crash cushion. And within those truck mounted attenuators, we focused on specifically figuring out if by taking the safety operator out of harm's way while retaining the necessary functions, can the risk of that particular operation go down by multiple fold and help make the work zone overall safer for not only the operator but also other participants in it. While the federal work zone statistics tell a story, the story in Ohio, as shown on the next slide, uh, also is the same way. The severity of work zone problem in Ohio, work zone fatality and injury and crash problem in Ohio is also uh, trending the wrong direction. And my next slide will show you a couple of statistics that tell the story again. As you can tell, work zones are some of the most unpredictable zones we have on our roadways. There were about 4,000 crashes last year, leading to 22 deaths within the work zones in Ohio. And well, more than that, every single injury fatality that has occurred in Ohio has led to a long lasting impact on our roadway construction workers, which represent a large work pool within the state. Uh, with about 5,500 people in state and over 100,000 people working in that domain nationally. Um, I know we all take work zone safety very seriously. We have 2026 National Work Zone Awareness Week, which was held between April 20 and 24, uh, was with that particular theme, safe actions, safe lives. We wanted to expand on that theme further and kind of put mechanisms in place that can naturally help with the safe actions portion of it, hence leading to saving lives in the future. As we move towards more smarter and connected transportation systems, it's important to kind of investigate and research how these tools are, what these tools are, how they operate, that and then we can then see if they have a place within our ecosystem to help improve safety for our workers who operate in the work zones every day. These benefits not only help touch the workers' lives more positively if the technologies work right, but also help drivers navigate those work zones more safely. I guess I'll leave with my last slide here and then transition over to uh, Rex next. Um, the biggest thing I wanted to communicate on this particular program is that these autonomous truck mounted attenuators that we have looked at in higher detail have been looked at in other states. The difference within the difference in this particular research program is it was focused on communicating a lot more with workers, understanding what their needs are, and then working very closely with the OEM to build technology that may be more fit to their needs. The research that has been done elsewhere has focused on understanding the technology and the operations portions, but has not really looked at transferring that knowledge into everyday operations for what the workers in that state may need. And here, through our research program, we focused on both identifying what the benefits were if you were to deploy technologies like these, but also solving some of those challenges um, that involve training of operators, lots of stakeholder engagements, and then slow and progressive deployment of technology so that everybody across the board is very comfortable with this technology as it's deployed. You will start to see a lot of that in our research project here and research findings. And I'm going to lean on Rex, who is going to share some of those findings next.
Yep. And to start with that, I just wanted to jump into who our personnel is that we put on this project. So we definitely had some of our best players out here on this ATMA personnel project. So starting off with Mohit, he is our principal investigator, and then myself as the project manager. But there are lots of other talented individuals involved on this project as well. So I wanted to make sure that Dr. Tim Seitz, he was involved with dealing with a lot of the development as we went through a lot of the testing on this project. Same with Sayali, Karen Jakar. And then we also have Wally Brown. Wally, he's been with TRC for a few years now, and he has a lot of experience behind the wheel of autonomous driving, different systems. So he was a natural fit to be in this project. Douglas Johnson, he's one of our research engineers as well. He was one of the main drivers throughout the testing of the project, and he also had help from Lokmanya Rampilia as well. So this is the key personnel that we had on the project. Like I said, we decided to put some of our best, brightest talent out here, so that way we could dive deep into the system and further understand it more. So looking at it from a more project structure as well with our partners, we did have other individuals involved as well, other than just TRC. So TRC's main focus was to basically, we house the facilities and the testing, controlled environment test grounds. So that's primarily TRC's function on this one, but we worked with Kratos as well. So some of you may know Kratos as more aerospace kind of stuff. So I was just at the Air Force Museum this weekend. So it's kind of funny. You see some of their technology that's out there. So when you immediately think aerospace when you see Kratos, but they also dived into this technology well. So they used some of their guidance technology and applied that towards this ATMA technologies. We also had the University of Cincinnati involved on this project as well. They helped us do some analysis work after we got some of our data as well. So we'll go into a little further details in the project too on some of the data that they pulled up. The timeline on this project was initially started to begin in October 19th, 2023 and end on February 19th, 2026. However, we did end up needing a 6-month extension on this project. That was due to investigations that we found inside the ATMA system. So as we went through our CE testing, we noticed that there was some some parameters that we'd like to further investigate into. So we applied for a 6-month extension, and that allowed us to get into a little additional testing. So if you look at the columns on the left, you'll see that the project was broken down into 5 tasks. Starting off with your basic tasks, just all project management being in task 1. So all activities inside of there, kind of like dealing with your startup meetings, your monthly status meetings, this final presentation, they all kind of fall within that category. So that runs the duration of the project. The first part of work on the project after you get past the startup was our viability analysis. We'll go into more details on what that is, but that roughly was almost the first third of the project. That was then followed by the technology selection and procurement. So working with Kratos, making sure which trucks we wanted to use, get them down to Kratos, get equipment installed, those kind of things. Task 4 is where a lot of the meat of the project was. So this is where we went into testing. So if you look at this, we had to develop a test plan, then followed that by CE testing. So initially we only had phase 1 and phase 2, but like I said, we wanted to jump in a little further, do a little deeper evaluation on the system. So we ended up going into a phase 3 CE testing as well. So that actually just concluded earlier up this year. So we're now in the final reporting presentation phase of the project. So new project end date is August 19th, so it's almost wrapped up. But then with that, we'll lead into how we actually started the project. So I'll give it back to Mohit here, and Mohit could start giving us a little bit more details on how we started getting into the viability analysis.
Thank you, Rex. A big part of the project, as Rex has briefly talked about, was to really dive into what our workers are exposed to when they operate on the roadways every day and conduct their everyday operations. And those conversations are a big part of why I think this project was successful. This leaned very heavily on involvement from District 6, District 11. Folks down at the District 6 Madison Garage were fantastic. We were able to do plenty of ride alongs and really understand what you all see when you go down on the roadway and try to operate in a busy highway environment. As you can tell here, we've documented about six garage visits where every visit we went in and rode along with the crew, observed the operation, observed the traffic behavior around it when there was an LEO involved, when there was not an LEO involved, and tried to understand what kind of constraints and safety considerations does the crew need to look at when they're taking this technology, taking a crash attenuator down on the highway. There were some moving operations, there were some stop and go operations that we observed, and there were operations that were on a highway like I-70, busy, multi-lane, high traffic volumes, high speed, as well as some state routes where it's a much narrower operation, narrower roadway environment, uh, and try to understand the challenges that involved in it, the kinds of typical operations our crews have to do when they um, go down and conduct maintenance and repair operations. Big shout out to all the crews at District 6 and District 11 who really helped us get a true grounding into what your everyday life looks like when you're operating out on the roadway. From these visits, we identified some of the common pain points and challenges you all see out on the roadway. And my next slide talks first about kind of the challenges you all see when you are on the roadway. You can see a couple of pictures of from the top picture. Here's us trying to take a sweeper out on the highway in the and doing a shoulder sweeping operation, debris pickup and shoulder sweeping operation on an I-70 just west of Columbus. you can start to see that these field visits have helped us fully understand and appreciate the variety and the complexity of environments that you all operate into, the narrowness of our roadways, the errant behavior of our traffic, which I'm sure you all are kind of fully aware of. And frankly, it's an eye opener for a research team like like ours. We should do a lot more of these visits so that solutions that the challenges are fully understood and potential solutions can be brought out of it. We noticed a couple of key challenges, right? There is one, um, taking a TMA out on a high traffic density roadway is a necessary operation. It's a very tough one to also coordinate the amount of crew and the amount of communication that needs to happen to do this all safely. uh, is magical to see. Every time I now see a TMA out there, I have a enhanced appreciation of kind of the challenging part, the insides of your job. And then as I travel through our roadways, there are many reasons why a TMA crew may appear occluded to traffic who may be approaching it. One, there could be roadway curvature related issues. There could be just purely drivers are driving distracted. Those things can really um, impede safety when you all operate out on the work zones. And there are then other aspects, like the roadways are narrow inherently. When you navigate on a narrow shoulder, you may have to cut in and out of the shoulder to allow for proper placement of the crash barrier. And those challenges were properly documented as we did our field visits, supported by the fantastic crew at District 6 and District 11. Now, from that understanding of challenges, on our next slide, we built a appreciation of what we thought our workers will need. We went, documented all of our understandings, and took it back to our TAC. And TAC was a really important sounding board in saying, yes, these needs are real. Yes, this is the right approach. And here are the top three things that we think this research program should tackle. So I'm kind of just listing off these worker needs. There was a resounding agreement that everybody needs to understand that TMA is a protective device that only works when we have the correct placement of crash truck and the work crew within the zone. They Everybody that we saw out there were kind of very cognizant of that. Our safety operators were also very much aware of traffic behavior, um, and they were constantly monitoring traffic as they flew by past the work zones. And then this kind of um, echoed the need for the amount of communication that's needed between the crash truck operator, like almost an understanding that's needed between the crash truck operator and the leader vehicle and the work crew, to make sure everybody in the zone is able to operate with the highest level of safety. Um, there there appeared to be a preference for the use of crash trucks that facilitate easy maneuverability within the work zones, and safety within the work zones. And then the biggest thing we heard from our workers down there was that safety is a really great motivator for help in adoption of new technology, but the technology should not be mandated. There should be a choice that exists. The technology should be made available, and then the choice should exist whether this is the right fit for that use in an everyday environment. I'm going to switch over to my next slide. Um, Based on these challenges that were observed in the field visit and our documentation of needs, we went out to the market and tried to find out what kind of potential technology candidates exist out there that will allow us to take the safety operator in the crash truck out of their seat while still maintaining the full functionality of positioning, communication between the two vehicles so that everybody in the crew can operate safely. We found two potential candidates. One, Kratos, the technology company we briefly talked about as Rex introduced the project. Um, the Kratos automated truck mounted attenuator is a retrofit kit, and you'll see that in a couple of slides. Um, Basically, the kit is designed to be installed on an existing dump truck. You have sensors and communication technology that allow for the two trucks to talk. And once that kit is installed between the leader truck and the follower truck, the safety operator has the ability to walk out of the follower truck and hop into the leader and control the follower truck from the leader kit. You will see that a lot in our program as I show you some results, and Rex will talk you through some of those results. Now, the best way to imagine this technology is this is like a leader and a follower platoon. Think of it as a long trailer that you can extend all the way back and control from the leader based on how much spacing you need between those two vehicles. It's a low speed operation mechanism. Our trucks, I think, were retrofit and uh, and only were operating at a maximum of 25 miles an hour during any of those operations. And it's a GPS based system. That means as long as you can see the satellites, you can see the leader truck put down a trace that the follower will just catch up to. The second candidate that we went out and saw in the market was is on my next slide. So that's a very similar system to the Kratos truck. It was designed and engineered by Virginia Tech. They have, to our knowledge, they have one of them operational in the state. But this system, while it uses the similar kind of approach, uh, it was not commercially available to us at that time. The leader and the follower are doing the same exact job, but there are a couple of benefits to having this system over the Kratos one, including the ability of the leader vehicle to be more. Um, you can swap out a couple of leader vehicles just because of the design of the leader box here. Um, and we looked into that system as well as Kratos's. And next slide, we eventually, due to the timing of the project, due to the availability, due to commercial support, we selected the Kratos system. Now, the Kratos system is commercially available. We retrofit it on our own ODOT trucks, generously donated for this project by District 6. The Madison Garage played a big role in selecting the trucks and sending them down to ODOT, sending them down to Kratos in Florida. Um, and then the biggest differentiator for us was having Kratos as a partner on the project. Uh, Helped us bring to the table lots of custom development needs that have uniquely then satisfied ODOT's projects. So I'll leave you with that. There are many other slides that talk about the system's performance. Um, and Rex, you can carry the conversation forward.
Yep. So next step on the project was once we selected Kratos, we needed to get the equipment installed onto the trucks. So what we noticed was this was going to be a 3-month retrofit. So that included installation of all the components and calibrating the system and then testing it at their facility. So we physically had to drive the trucks down to Florida. So that was a long drive for those guys in a dump truck. So really appreciate the work they did on that one. So, but once we got it down there, we said the trucks went through the retrofit process. Kratos, they can adapt the system to any kind of truck. So whether you have like an international or a different model truck, you're able to retrofit to that. So they had to 3D scan all those 3D scan the trucks in order to design custom sensor racks and mounting hardware for their equipment. So if you look at the bottom of the slides, or the bottom of this slide for those 3 pictures, you can kind of see a layout of some of the equipment that they put on these trucks and that they have to retrofit on there. So if you look on the left side pictures over here, those are the lead vehicle components. So the lead vehicle is it's not as complex of a system, but it still needed a rack system mounted to the top of the truck. It needed custom panels with an HMI in the front of the truck, and then also the box that holds a lot of the equipment that's in the back of the truck. All this stuff is removable, so if you do have to do a decommission, which we'll discuss later, that is possible. Pictures on the right show additional equipment that was used for the trucks. So there's devices that can be retrofitted to the steering wheel to make sure that the steering can turn. There's LiDARs that are added to the trucks, emergency stops, and actuators as well to help control like throttle and brake, so that way the truck can stop and go in those situations. During the installation, we did run into some component delivery schedules conflicts for multiple vendors, but due to that, we still were able to hit that 3-month retrofit. So it's possible it could be accelerated, but it's one of those things where you have to get the trucks down there and then get some of the equipment ready for it as well. So with that, once we had the equipment installed on the trucks, that's when we get into a lot of the fun of the project, the controlled environment testing. So this is where the team really wanted to test the system out and just make sure that it hit these operational guidelines. So for instance, we want to make sure that the system's safe. You want to make sure that it has the ability to start, to stop, and also resume its operation safely. The other thing we want to make sure is that the follower responds as intended. So that follow vehicle, you want to make sure that if the lead vehicle is doing something, you want to make sure that it's accurately following. So that lead vehicle, it drops what we like to call digital e-crumbs, but think of it kind of like breadcrumbs for like Hansel and Gretel finding their way through the forest. Like this is the digital version of that. So it basically picks up these e-crumbs that the lead truck's dropping. So we want to make sure that if there's any changes in that, we're monitoring it. Other things are there's obstacles out on the roadways. So you'll have barrels, other vehicles, those kind of things, people working. So you want to make sure the obstacle detection system's working. And then also we want to make sure that the operational tests, similar to what you'd see in the roadways, we're simulating that as well. So if there's certain scenarios that we wanted to check into, we want to make sure we built those into our test plan and test those out. So some of those features that we wanted to test into were built into these charts right here. So good news is you got all check marks. So the system passed a lot of the things that we were looking at. So some of the first ones that we'll talk about is an A-stop functionality. I have a video on the next slide that I'll show you that goes a little more detail what that is, but it's basically one of the stop features for the ATMA system. The other one that you want to check is make sure that it has an emergency stop function. So there are external devices on the trucks and there are internal devices. So you want to make sure the people inside that lead vehicle are able to test that as well. And then for the safety operator override, you want to make sure that can happen as well. We also have the lead vehicle. There's also another stop feature. It's called a pause mode. And I have a video of that we'll show. So there's several different kinds of stops, and I'll kind of describe later why you want to test each of these. But then we also have loss of signal. So since this is a GPS unit, there are obstacles out there in the world that will block the GPS. So you want to make sure what happens if you do lose signal for any reason. You want to make sure that the system does its intended reaction. Other things that we wanted to test for were the vehicle gap accuracy. So you do have the ability to set the distance on this on these trucks. So you can set it anywhere, I believe, between 25 feet all the way up to 1,600 feet. So it has a very wide range. You can set that gap. So we want to make sure we could test that and make sure that it is accurate. And what the gap is you command is the gap that you get. We also want to make sure if there's a change in vehicle gap, that we're monitoring that as well. You are able to offset this vehicle by 12 feet left and right. So basically about one lane width. So if you are intending to offset the vehicle, that the lateral offset function does work. And if there's a change in the lateral offset, that while you're in operation, if you need to change that, it does your intended action. If the lead vehicle speeds up, slows down, those kind of changes, we want to make sure that we could go through those. And then same with lane changes as well. So overall, like I said, the system passed all these parameters, and it's something that we tested very thoroughly over the past few years. So this video right here, I'll go into a little bit of what the A-stop function is. So the A-stop function, I'll play the video. You'll see here we did a little picture-in-picture. So A-stop is not a, it's not an emergency stop. I'll show you the difference between the two. This one's just a commanded stop inside the system. Sometimes you just need the system to stop, but you'll have to re-engage it manually is the main thing. So like for instance, if you have an obstacle that comes in between you guys, it needs to stop, but you don't have to do a hard reset on everything when you do this stop. You can simply clear the code on the HMI, which is the little tablet screen that you can see above the buttons up there, and then you can go back to resuming operation. But most of the time, yeah, the A stop function, we have other stop functions as well. But this one, it's not a complete e-stop. So the e-stop is the one that a lot of people would assume is the main safety kind of stop. So for instance, if something were to run out between you, a road worker walks between the vehicles and it's just too close of a call, those kind of situations, whatever situation you need to run into hit an e-stop, you could do that. Or if you're having undesired behavior from the truck, you could e-stop it that way as well. So you'll see here, this one does basically throw the anchor is what I like to say. It will lock the brakes, it will shut the engine off, and it will engage the parking brake as well once it gets to a stop. It does try to gradually stop. It does not just automatically just stop everything, kill the engine in that moment. Once it gets to a certain parameter, then it kills those kind of things. But overall, the difference between an e-stop an A-stop, like I said, you'll have to do a hard reset of every system after you engage an E-stop, whereas it's more of a soft reset when you have the A-stops. Another stop feature that we have is called a pause feature. So this one, think of it as you come up to maybe a stop sign, for instance, like you'll see in this video. You want to make sure that the follow vehicle stops. Well, if you keep going after you stop, the truck needs to physically stop. It's not going to register that EECRUM said, oh, you stopped here for 30 seconds. No, I'll stop for 30 seconds. You have to manually control that. So what you can use is a pause function. So the pause function on this truck, you can temporarily pause the truck, and then it'll start picking up those EECRUMs again and start following the truck. So in this situation, on this video, we wanted to demonstrate coming to a stop sign and completing a left-hand turn in case a vehicle had to cut through. So typically, if that vehicle had to cut between and the system was engaged, that would trigger an A stop because there would be a vehicle that passed through during an obstacle detection. So in this situation, if you paused it, it didn't have to go through an A stop situation. Next feature that we have is called an idle feature. So this one is similar to the pause. However, it does not start picking up the EECRUMs. So this is very useful in case like something falls off of a vehicle and you have to pause and go back and get it. Or if you just notice there's something on the side of the road and you don't want this truck to follow your path. There's multiple reasons that you would use the idle feature. But once you engage it, that follow truck stops and it no longer is picking up the EECRUMs that the lead vehicle is leaving behind. So in this video, you'll see the driver is circling the truck and then he'll have to get back to a point to the truck to kind of retether with it to re-engage the system. So once you reestablish your points with the truck again, it'll start picking up the EECRUMs, and then you'll be able to do your rollout procedure and move forward again. So other areas that we tested these trucks in were obstacle detection and operational tests. So we had some scenarios where we like to use pedestrian targets. We'll use vehicles that cut in. We will use soft targets, barrels, cones, those kind of things. So in these kind of scenarios that we tested, we wanted to make sure that the work vehicle could detect multiple things in these scenarios. So if you have an obstacle, for instance, while you're doing a lane change, you want to make sure that the truck, if it picks up between there, that it'll actually come to a stop. So like I said, walking through these scenarios, you'll see that if there's an obstacle in a curved lane, past that scenario, we need to make sure we test that multiple times, multiple distances. So if things were to the left or to the right, just any scenario that you could think of, we wanted to make sure that the obstacle detection worked. Because most of the time, these trucks are going to be following road crews. So we just want to make sure if there is anything that gets between the two of them, that it could detect. Things that we also noticed too is that operation through nighttime worked just as well as it did in daytime as well, due to the LiDAR sensor on the front. So one of the scenarios that I also want to go through is a lane change scenario. So ODOT did request us to investigate this. This is one of those things as you start going through testing. It may not be in the original test plan, but it just pops up that we wanted to check and see. So this scenario, we wanted to make sure that the vehicle, if you needed to merge, for instance, on a lane, or just do a lane change itself, you want to make sure that the vehicles can do that safely. There's lots of challenges to this, as you can imagine. You have vehicles approaching, for instance. You may not be approaching the lane of traffic they're traveling in, but you still want to do it safely. There's lots of factors that go into this. So we wanted to make sure that we tested thoroughly in this. So what we tried to do is there's no preset settings inside the system. You kind of have to use the tablet system to navigate this. So there is, in this scenario, we do have a safety operator behind the wheel, but just imagine it's fully being controlled by the person in that lead truck. That person in the lead truck's position, they're in the passenger seat. So think of it as the driver being rotated into the passenger seat of that lead truck, the driver of the follow vehicle being rotated into that passenger seat of the lead truck. So they're the ones that are physically hitting the buttons, making it go left and right. So you have to do that real time. You do it in 1 foot increments. So you kind of have to shift as you go, and you have to be in coordination with the driver. There's lots of factors into this one. So I'll go into a little bit of the safety concerns on doing this scenario, and how ODOT feels about that. So and how incorporating these into the operational domains of this. But like I said, it's one of those scenarios that pops up as you're going through testing, that we just dive in, do a deeper evaluation, and make sure that we understand all of these things before you actually take these out onto a public roadway. So after testing it concluded, you'll notice on the timeline that we said we had 3 phases of testing. So we had phase 1, phase 2, phase 3. Those all happened within 3 different years. With that, the reason needing to stop testing is that these are ODOT salt trucks. They do need to be used during the wintertime to deploy salt on the roads. So with that, we needed to make sure that the system can be disassembled. So we wanted to make sure we could do a proper decommission on these trucks. Thankfully, we got a lot of testing on this. We got to do that in two iterations due to the testing. So we had to remove as many components as possible to make it easier for the salt truck operators to use the trucks again. So like I said, there's equipment that's been retrofitted to the steering wheel. There's actuators that connect to the brake and gas pedals on these trucks. But then you also have the GPS equipment and LiDARs, those kind of things. LiDARs are expensive pieces of equipment, and you don't want to get those damaged out in salt times. So we had to walk through the system, make sure we took off everything that made sense to take off, and make sure that it was safe during wintertime. But you also don't want the problem of doing a full decommission, completely removing every component, because that just adds extra time and labor during a recommission. So like I said, our team, we went through, we worked with ODOT District 6 and 11, got their inputs on it. Wanted to see the driver of the truck that uses it during the wintertime, how he felt comfortable, what equipment we could take out. So we made sure we had input from that as well. And they said some of the components we're able to leave on. The top left picture there, you'll see the actuator that's mounted behind the seats. We were able to leave that component in place, which takes a lot of calibration into factor. So you want to make sure that those kind of things are not tampered with too much. So it makes your reinstallation a lot easier. So leaving that in place makes the recommission a smoother process. But we also noticed, though, after decommissioning, picking the right components to take off the trucks, putting it back on, you do still need to do a little bit of calibrating of some components. And thankfully, we were able to have support from the vendor on doing that as well. The vendor was able to come on site one year to help us, but then we also wanted to make sure we were able to do it remotely as well. So the vendor tried to help us out as much as possible in getting everything set up remotely as well. So I think after the first decommission year, teams were able to do very well getting the system taken off and put back on. We did have a few hurdles. There's just wear and tear on items too. So it's a good time to, during the decommission process, to look through everything and make sure if there are issues that you're documenting that during your decommission. But there's also, just like any other truck, you want to make sure during your startup procedures as well that you're every time you use these trucks, you go through and look at each component and make sure that everything is safe as well. So, but yeah, you'll just notice during the duration of the trucks being used during winter time, that salt operation can be very hard on some things. So some things may rust, maybe not on the ATMA system itself, but on the truck itself. So those kind of things you just have to pay attention to during your recommission. Another aspect of this project was media exposure. There was a lot of publicity on this project that was shared out there, a lot of exposure, and it's for a good cause as well. So the more these trucks got used, the more understanding that we gained of these trucks working through the system, the more we share with ODOT, the more that this information got put out to the public as well. So there's lots of perspectives that you guys could look at on this one. So throughout Ohio, you'll see that the Columbus Dispatch, several news stations reported on it. There's YouTube links to it as well. So you'll see on the next slide, there should be slides available to you as well. So if you need links, this slide right here, you should be able to test some of these links just in case you wanted some more information from some of these sources to see how the trucks went through the testing. Okay, but so jumping in after the testing, we wanted to talk a little bit about our findings on this project as well. So the lane change scenario that I was talking about earlier that I showed the last video on, this one, I just want to make sure that we communicate that ODOT, due to their recommendation, they do want to make sure that these scenarios are not performed during their operations. So we're just evaluating, but it's one of those situations where during our evaluation, you understand the difficulty that it is to do. Once you get trained on it, it's not too difficult to do, but there are rooms for error. So anytime there is something like that, it's definitely better to err on the side of caution on this one. The idle buttons. So there was, during the idle mode, once the idle button was engaged, the system no longer controlled the steering, the brakes, or the accelerator. If the safety driver wanted to intervene that system while the system was in idle mode, the system will still try to match the headway and acceleration, which could be unsafe. So the idle mode, you definitely want to make sure that you switch the truck to idle mode if there is a safety operator inside of the truck and they want to do a control. So that's something that you want to make sure when you're going through your training with your operators, that they know that their first instinct is not to smash the brake, not to turn the wheels. It is to flip the switch to idle to do that first. So it's just one of those things you have to go through your training. So that's one of our safety critical findings that we wanted to make sure we shared with ODOT as well. Intersection operation, that's another recommendation. We showed the video earlier on the trucks going through the intersection, like using the stop sign and the pause feature. However, there are critical components to that: visibility, complexity of certain intersections. So it's just best in that situation that to treat it safety critical and make sure that these systems probably should not be used going through an intersection. And working with ODOT, that was the recommendation that they wanted to test with moving forward as well. Underpass driving is another thing. So this system does use GPS, and that GNSS signal, it does get lost when you go in when you do go over an underpass. What happens next is the system goes into what we call a dead reckoning, and that is how it navigates while the system's lost. That works for on this system for 60 seconds, and it should guide the system using inertial navigation. However, we did notice that there were some issues with this. So we wanted to make sure that if there were any issues with that dead reckoning system, that the underpass, while taking it out on roadways, the system is disengaged and manually moved under underpasses temporarily till further evaluation. We have been working with the vendor on that. So the vendor has been absolutely fantastic on making progress on making this better. So it's very close to working well. So it does work in scenarios, but it's just one of those things. If it's not hitting 100% all the time, it's one of those things where we're just flagging just to be safe. Other findings that we found for hardware software improvements, we noticed there was a lurching behavior with the trucks. What would happen is sometimes the truck would lurch forward when the trucks came to a stop. So the lead vehicle came to a stop, the follow truck would sometimes lurch forward. We worked with the vendor, that issue was fixed. We were also able to fix turn signal and LiDAR warnings. There were times where you'd have the turn signal on and the audible warning would still be there. It should not have been. So we worked with the vendor, that got fixed. There was a gap distance of 100 feet for the POV. We wanted to make sure that this was also fixed. So basically, POV is an intrusion vehicle. So if there was a vehicle to cut in between the two, the gap would automatically set to 100 feet instead of to the commanded gap distance. So we would make sure that it did set to the commanded gap, so that was able to be fixed. A stop for the POV, this one we were able to get fixed partially, but what would happen is if there was an obstacle between the leader and follow, it would come to an A stop. Sometimes the vehicle should just pause. So we noticed that if you're cutting in motion, the vehicle would work, but sometimes if it came to a complete stop, it wouldn't work as intended. So we worked with the vendor, that is fixed partially, so there's still a little bit more development to be made on that. The overpass test, as I described earlier, said when the system falls into that dead reckoning, it still needs a little further development. And then obstacle detection on a curve. We noticed in this scenario, if you're on the left lane, which is rare on a left curve, if there is an obstacle 2.5 feet within that lane line, the vehicle should stop on that one, but there had to be intervention on that one. So that is that it's a very rare scenario, but those kind of things could still take a little more development. Demonstrations, hit on this one real quick. We made sure that we took these trucks out and got feedback from ODOT's garages. So we went to District 6, District 11. We had um, people come out to our facility as well to view the system. So it got a lot of publicity there. Initially, people did not. Some of the road workers were not initially impressed with the system when being described to them. They wanted, after taking the time, getting them in the seats of the truck, walking through, letting them know that that follow vehicle's driver is just physically being taken out of that truck and moved into the lead vehicle's truck. That initially really changed the perspective from them as well. And after once they saw the trucks in operation, they were really happy to see these trucks. And most of the people that we talked to, they really wanted to see these trucks put into operation. And then a cost benefit analysis was also performed by the University of Cincinnati. Biggest takeaway on this one that we've noticed is that the closer you get to the longer the duration of this, the better the benefit cost ratio is on this one. So what we were typically seeing on this one, there's two different approaches: reduced crash severity and reduced operator exposure and labor cost savings. Both of these approaches, we've noticed that once it starts to exceed that 9 years, is really where it starts to go over that 1.0 number. And with that, I'll let Mohit finish out on recommendations. So Mohit, if you want to.
Yeah, thank you, Rex. That was a comprehensive deep dive on some of the activities that have happened over the 3-year project. We looked at a few recommendations, putting together a few recommendations, and I'll paraphrase some of what's listed on this slide. One, from an installation perspective, um, the more standardized this system and our choice of vehicles is, the easier it is for the DOT and the vendor to work together to scale this system across the fleet. That's a one key takeaway from the exercise of both installation, first time installation, decommissioning, and recommissioning. The more standardized things look, the easier it is for us to all kind of scale the system up. From an operationalization of this technology perspective, um, in our experience, the most important thing here is to know your operating domain, the domain in which these vehicles are required to operate, the kinds of traffic behavior they'll see, as well as know fully and thoroughly what the vehicle's capabilities are. You don't want to be put in uh, vehicles in a situation where they were not designed to be. That's just setting the overall crew up uh, uh, for not for success. But even when you have those two key pieces of knowledge, your operating domain figured out, you want to have a phased approach, really. You want to crawl, walk, and run. You want to test the waters and slowly build comfort and confidence in your crew um, as they take this system out on public roads. The key aspect of that is procedures and training are extremely important. And coming out of the research program, we worked very hard on improving some of the training processes, the documentation that the system came with, so that everybody who touches the system has a comprehensive knowledge book that they can lean on as they start to take this system out on public roads. And finally, kind of vendor support is still important as you start to talk about long service life for this vehicle, for the cost benefit analysis to work out. And the vendors are typically the vendor we have had the fortune of working with have been very responsive. They want to see this system become successful, save lives out on the public roadway. I think um, it just speaks to everybody's motivation of putting systems out that are long term, well supported, as well as have a positive impact on the safety problem that we see out on work zones. I'll leave everybody with those key takeaways from this research program. And Kara, I'm going to turn it back over to you folks to see if there are any questions for us as we come close to time.
Wonderful. Thank you so much, Moet. Let's see here. Well, we have had just two questions come in throughout the presentation, and they were answered um, rather quickly. So if anyone has any questions that they would like to submit really quickly, we are happy to take them. Okay, let's see here. Well, we have um, messages of appreciation for you all for this wonderful presentation. And someone is asking about a roundabout. So have these been tested on roundabouts? I think that might be what this person is asking.
Um, so physically on a roundabout, we have not, but we do have space on our facility to where we test around curvature, like roundabout systems. So we do have like a flat pavement section um, that is built into our smart center that's to simulate roundabouts. So we were able to test around curvature like that as well. So uh, we would apply a lot of our curvature data to what we would do for roundabouts.
Wonderful. Y'all thought of everything. Let's see here. We have one last question we will go ahead and ask. And that question is, are the trucks still equipped now that the project is ending?
Yes. So currently, yes, the trucks still are equipped. Um, I said we still have till August 19th. So there may be some scenarios where we might be able to run out and grab one more scenario. So until we hear more, we are just leaving the trucks equipped.
Makes sense. I know that I've been interested in these. I've seen the media talking about it and everything. I've seen talks about it at a couple of different conferences and everything. So I'm very grateful that I got to be the person that hosted this webinar today. But that is all the time we have for questions today. So, on behalf of LTAP and ODOT, I'd like to thank Moet and Rex once again for sharing their valuable knowledge and expertise with us. As mentioned earlier, the recording of this webinar and PDF of the slideshow will be shared with all registered attendees within the next week. If you are logged in and present for the full duration of the webinar, you will receive a certificate of attendance within 5 business days. Before you leave, we'd really appreciate your feedback. A very short 4-question survey will automatically launch in your browser once the webinar ends. It only takes a minute, and your input helps us improve future sessions. So thank you all for attending. We hope you found this webinar informative and engaging. Have a wonderful rest of your day.